Now that we have a little bit of a basis for vectors, let's step back and talk about motion in one dimension. This could be either the x direction or the y direction, or a combination of the two but along a straight line. Keep in mind that we get to choose where our axes are, so whatever this direction is, that will be our x or y axis. It's just a matter of choice as to what letter designation you want to give it. So the first thing we want to do is talk about position. We're going to define a position as a location along a number line. To the right of the origin we'll call positive, and to the left we'll call negative. Or it could be up and down. Above the origin might be positive, and below the origin might be negative. There are several different designations for the position along the number line. Those designations will oftentimes include x, r, or s. For the sake of argument, for a little while, at least in this class, we'll be using x, but we'll use r and s, depending upon the circumstances later on. So where you are along the number line, that's your position. So we're going to define displacement as the change in position in moving from position number 1 to position number 2. So if you haven't already been introduced to the Greek letter delta, it just looks like a triangle, and it means change, and we're going to use the Greek letter delta very often in this course. So delta x means the change in position. So here I am at the beginning of some time, and here I am at the end of some time. And my displacement will be my final position minus my initial position. And I designate that here as x2 minus x1, but any subscript might work. But this is always, x2 is always the later position. So let's take a standard number line to the left and to the right. And here's my origin. And here are some other positions on that number line. And maybe I start here. So if that is my initial position, x1 is equal to 3. And if at a later time I am here, x2 would equal negative 1. Then my displacement from the right side to the left side is my delta x. And in this case, delta x equals x2 minus x1 equals negative 1 minus 3, which is negative 4. And if you think about it, that makes sense. I moved 1, 2, 3, 4 units to the left. So I have a displacement of negative 4. I haven't attached any metric units or English units to this value. It doesn't really matter at this point. Now if at a later time I move to the left one more spot, maybe this is x3, then in here I have a delta x equal to negative 2, because that's what x3 is. x3 is negative 2, minus a minus 1, and that's equal to negative 1, meaning, of course, I moved 1 unit to the left. And then if at a later time I go from x3 over here to 2, then that new delta x might be equal to 2 minus a minus 2, and that would equal 4, because I've moved 1, 2, 3, 4 units to the right. And after all of these displacements, I might talk about a delta x that's equal to x4, which is right here. x4 is equal to 2, minus x1, that's my overall displacement, and that would be 2 minus 3, which is negative 1. So I have moved 1 to the left. So my displacement there is negative 1, but if you look, I have moved 1, 2, 3, 4, 5, 6, 7, 8, 9 units. So my distance that I have traveled is equal to 9 units, but my displacement from 1 to 4 is only negative 1 units. So be very careful about the difference between displacement and distance. They are two separate things. Displacement, by definition, is a change in position. And distance, there's more of an absolute value sign somewhere in there. It's a little more complicated, but I want you to keep that in mind, that distance and displacement are different things. So here we defined average velocity and speed. Now average velocity is equal to a change in position, or a displacement, divided by a change in time. Now here I've designated it from 1 to 2, but what's important here is that the subscript here and here are the same. In other words, x2 corresponds to some time t2, and x1 corresponds to some time t1. This could be x4 minus x6 divided by t4 minus t6. It doesn't matter. But what does matter is that these two have the same subscript and these two have the same subscript. The other thing you might notice is if I'm talking about a graph, time along the horizontal axis, position along the vertical axis, then x2 minus x1 at t2 and t1, this actually represents 2 points, and x2 minus x1 represents the rise, and t2 minus t1 represents the run. So this average velocity is the slope between 2 points on this position versus time graph. Okay, so when I say x versus t, that's position versus time. Speed, in contrast to velocity, is distance over time. So if we go back to our previous example, my average velocity here was -1 over some time period. Let's call it 9 seconds just for the sake of argument. So -1 over 9. That's not very fast, but my speed was 9 units over 9 time units. So 9 distance units over 9 time units. This is equal to 1. So my average speed was 1 unit per second, but my average velocity was not. Average velocity was -1 over 9. So speed is distance, velocity is position change or displacement over time. Now we're going to see that a lot of motion sensors will graph position versus time for us, and we'll actually look at these relationships during the class period. So let's take a look at an example. So we have a trip from Laramie to Fort Collins, and we're going to assume that is a distance of roughly 80 kilometers, and you're driving down the road at 80 kilometers per hour. So here's Laramie. I always like to draw a picture, and we're traveling to Fort Collins. And this is 80 kilometers from one point to the other. So from our starting point to our destination is 80 kilometers. So 40 kilometers into the drive, we've come across some construction. So we make it to here. This is a 40 kilometer distance so far, and we come across some construction. And the construction causes us to slow down. And so we have to slow down to 40 kilometers per hour for the next 20 kilometers. So now we're here. So 20 kilometers. And for this part, we're traveling at 40 kilometers per hour. And again, over here, we were traveling at 80 kilometers per hour. Now, what I'm hoping is to average 80 kilometers per hour for this trip. So the question is, for this distance here, what speed do I need to travel? All right, so I want to average 80 kilometers per hour. Now, I was doing 80 for the first 40 kilometers, but for the next 20 kilometers, I had to slow down to 40 kilometers per hour. So at what speed do I need to travel? So my average speed is 80 kilometers per hour. How fast do I need to go in here? So let's call this the velocity over the third time period. All right, so I'm not going to tell you what that is. I want you to bring your answer into class on a little piece of 3x5 card or something like that, a small piece of paper. All right, I'm not going to tell you what the answer to that question is. I want you to bring your answer in and how you got that answer. Okay, instantaneous velocity is a little different than average velocity. In the case of instantaneous velocity, what we're going to do is we're going to take our average velocity, so that's right here, delta x over delta t, so displacement over time, that's average velocity. But to find an instantaneous velocity, what we're going to do is we're going to reduce this delta t down to smaller and smaller increments. And what that means mathematically is we're going to take a limit of this average velocity. We're going to take a limit as the denominator goes towards 0. So those of you that are into calculus already, you probably have a little feel for what this is all about, but we'll explain it a little bit here in just a bit. We're going to call that the derivative of x, or position, with respect to time. And in the world of physics, we don't like to write dx dt all the time, so we write x with a dot over the top. Now in calculus, you're going to come across derivatives and you're going to label a function as f of x and its derivative as f prime of x. Anytime we're talking about a time derivative, we use this dot notation. So the prime notation goes to a derivative with respect to whatever that variable is in here. The dot notation is very specifically a derivative with respect to time. And that's the notation we'll be using throughout this course. So what do I mean by a tangent on the x versus t curve? So let's assume that I have some function, and it might look something like this. We want to find out what's the velocity right here at this point. Now we know from the discussion on average velocity that it's a rise over a run. So let's assume I'm going to take a later point over here. This might be t2 and a position x2. Okay, remember t is along this axis and x is along that axis. And over here I have a t1 and an x1. Then there is a line that connects these 2 points. And the slope of that line can be discovered from this triangle. Here's delta x, here's delta t. And so the slope of this green line here, that slope is delta x over delta t. We call your designation in mathematics m as a slope. That's the average velocity. But tangent to the curve, tangent means just touching. So there is a line that just touches the curve. This purple line just touches the curve at that magic point. But what you'll notice is this green line has a slope different than the purple line. But if I reduce delta t, if I take a smaller point here, in other words, this is a smaller delta t, there's a slope between these 2 points. And this orange line here has a slightly larger slope than the green line and a slightly smaller slope than the purple line. So the green line has a lower slope than the orange line, but the orange line has a smaller slope than the purple line. So as I go from the green line to the orange line, I'm getting closer to the slope of the purple line. And what you'll notice about the orange line is its delta t, the orange delta t if you will, is smaller than the green delta t. So what's happening is delta t is smaller. And what I want to do is I want to make it smaller and smaller and smaller. What that means is I'm making delta t tinier. Delta t is approaching a size of 0. And when I get to that size of 0, and it's a limit, you never quite get there, when I get to that size of 0, I will have the purple line. So I could choose another line. So let's choose a point here, this blue point, and you can see that the blue curve has an even better representative of delta t than the orange curve that's been raised. Getting closer, and what do you notice here? The delta t for the blue curve is even smaller than the orange curve, which is smaller than the green. So the delta t has gotten smaller and smaller. That's what I mean by a limit, as delta t approaches 0. Alright, so let's take an example. Let's say I've got a curve, the red curve that you see here, on a position versus time graph. And this is some parabolic function. So maybe that function, x, is a function of time. Notice my notation is not f of x, but it's very similar. Position is a function of time. And let's say that that position as a function of time equals t squared minus 4t plus 3. So there's my position as a function of time. And what I'm interested in is what is my slope? What is my slope right here when t is equal to 3? What is the velocity of my particle at that point? And remember, that velocity is going to be tangent to the curve, just touching the curve at that point. Well, so the idea is that I take a position at a later time, let me call it t plus delta t. In other words, here's t, and then at a later time I'm over here, and this will have some delta t. That will be the delta t width. So what is this position right there? Well, the position is x of t plus a later time delta t. Well, if I said what's x of 5, you would say that's 5 squared minus 4 times 5 plus 3. That is, you put 5 in wherever you saw a t. So x at t plus delta t is just going to be t plus delta t squared minus 4 times t plus delta t plus 3. And then I'm going to subtract from that x of t. But that's just t squared minus 4t plus 3. So we're going to subtract those two. And if I do that, I'm going to get t plus delta t, quantity squared, minus 4 times t plus delta t plus 3. That's the first term, minus t squared minus 4t plus 3. That's the numerator. The denominator is going to be t plus delta t. That's the time in here, and then the original time was t. And eventually we'll set t is equal to 3, but let's just do this first. Well, so let's multiply it out. I get t squared plus 2t delta t plus delta t squared. That's just this part right here. Minus 4t minus 4 delta t plus 3. So I've done everything inside of that bracket. Then I'm going to subtract t squared minus 4t plus 3. I'm subtracting all of that. And then the denominator here is very simple. It's just t plus delta t minus t, so that's just delta t. So as I examine all of this, I'm going to get t squared plus 2t delta t plus delta t squared minus 4t minus 4 delta t plus 3 minus t squared, and now I'm at this term, plus 4t, because a minus and a minus gives me a plus, and then minus 3. So I've got a minus 4t here and a 4t there, those go away. I have a plus 3 and a minus 3, those go away. I have a t squared and a minus t squared, those go away. And I'm left with 2t delta t plus delta t squared minus 4 delta t. Now that's the numerator. Remember, the denominator was just delta t. And so I'm left with 2t minus 4, because delta t underneath there cancels, plus delta t. So that's this term. There's that term. But remember, it's the limit as delta t goes to 0. And as delta t goes to 0, that goes away. And I'm just left with 2t minus 4. So that's the slope of this tangent line. And when t is equal to 3, that's 2 times 3 minus 4, which is 2. 6 minus 4 is 2. So the slope of this line is 2. And if I went to a different point, say here, the slope would be different. As a matter of fact, that point, the slope is going to be 0. It's time to define a term you've used before, but not necessarily correctly. So we're going to talk about this new term as acceleration. So whatever you think acceleration might be, we're going to redefine this for you. So I'm going to say that acceleration is how fast changes. Well, how fast is your speed? So acceleration is how quickly does your speed change. So this is a change in speed, or a change in velocity, to be more precise, with respect to time. So it's a slope of the velocity versus time graph. So the average acceleration, so you notice I put an AVE here, the average acceleration is a change in velocity over a change in time. So change in velocity over change in time. Notice again, these subscripts have to be the same. If I ignore this equal sign here, if I take the limit as delta t approaches 0, then my average velocity becomes a derivative of velocity with respect to time. For those of you who had some calculus, since that's a derivative of velocity, but velocity is a derivative of position, this is the second derivative of position with respect to time. And so I'm oftentimes going to note that with an x double dot. First derivative, second derivative. So x dot is velocity. Acceleration is the derivative of velocity with respect to time. So v dot, which is the second derivative of position with respect to time. We're going to talk more about the calculus later on. What I really want you to concentrate on right now is just this first part. Average acceleration is a change in velocity over a change in time. Again, that equal sign is not correct. So a change in velocity over a change in time. That's an acceleration. Now velocity, keep in mind, is measured in distances divided by times. If I look at the units here, a displacement is a length and a change in time. So velocity has a dimension of length over time. So in the metric system, that might be meters per second. In the English system, that might be feet per second. Kilometers per hour, miles per hour, or other methods of measuring that. That's a length over time. So if velocity is length over time, and my change in time is time, then acceleration has dimensions of length per unit time over time, or length per time, or length over time squared. Now I really like this one better. So for example, meters per second, because when I say that, I'm really emphasizing it's meters per second, that's a speed, per second. So I'm talking about a change in speed or velocity, more precisely velocity, a change in velocity with respect to time. So meters per second, and I pause there on purpose, really emphasizes that it's not a speed or a velocity, because there's another second there. If I say meters per second squared, and I will oftentimes, I want you to really pay attention to that squared and not just ignore it. It's too easily ignored. But if I say meters per second, then it's emphasizing, hey, that's not speed. That's something different than meters per second.